In 1949, the Lima Locomotive Works unveiled a compact diesel switcher that, on paper, checked every box American railroads were looking for. It was rated at 1,000 horsepower, built with the same precision machining that had made Lima's steam locomotives legendary, and designed specifically for the yard switching and industrial service that formed the backbone of railroad operations. The LS-1000 should have been Lima's foothold in the diesel era. Instead, it became a footnote, a well-engineered machine that arrived just as the market had already made its decisions. This isn't a story about bad engineering. The LS-1000 was a solid locomotive. This is a story about timing, corporate structure, and the brutal economics of an industry in transition. Lima had built some of the finest steam locomotives ever to run on American rails, the superpower designs, the Berkshires, the massive articulateds. But when the diesel revolution came, Lima was caught between what it knew and what the market demanded. The LS-1000 was their answer. It just came too late. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. To understand why the LS-1000 failed, you need to understand what American railroads looked like in 1949. The industry was emerging from World War II exhausted. During the war years, railroads had moved unprecedented volumes of freight and personnel, often running equipment around the clock with deferred maintenance. Steam locomotives that should have been shopped were kept in service. Tracks that needed renewal were patched and pushed beyond their normal lifespan. By 1945, the physical plan of American railroading was worn out. At the same time, operating costs were climbing. Coal prices had increased. Labor costs were rising as unions negotiated better wages and working conditions. Water treatment, ash disposal, and the sheer manpower required to service steam locomotives were becoming economically untenable. Railroads looked at their balance sheets and saw diesel as the solution, not because it was romantic or exciting, but because the numbers made sense. The diesel-electric locomotive had proven itself during the war. EMD's FT freight units had demonstrated that a diesel could haul tonnage across mountain grades reliably, without needing water every 100 miles or coaling facilities at division points. The maintenance intervals were longer. The availability was higher. Most importantly, diesels could operate in multiple unit configurations with a single crew, effectively doubling or tripling power without doubling labor costs. But in the immediate post-war years, railroads weren't rushing to dieselize their mainline freight operations. That would come later. What they needed first were switchers. Yard operations consumed enormous amounts of locomotive power, sorting cars, building trains, shuttling cuts between classification tracks. Steam switchers were everywhere, but they were expensive to operate. A steam switcher needed a fire lit hours before it could work. It needed constant attention from a fireman. It needed water, coal, and periodic ash cleanout. For yard service, where a locomotive might spend hours idling between moves, the economics were terrible. This is where EMD made its first real penetration into railroad operations. The SW1, introduced in 1939, was a 600 horsepower switcher that proved diesels could handle the repetitive, stop-and-go work of yard service. By the late 1940s, EMD had refined the design with the NW2 and SW7 models, both using the legendary 5867 engine. These weren't exotic machines, they were workhorses. Railroads bought them by the hundreds because they worked, they were reliable, and EMD had built a service network that could support them. Alco had followed EMD into the switcher market with their S-Series, the S1, S2, and later the S4. These were competitive machines using Alco's own 539T engine. Baldwin was also building switchers, using engines from De la Vergne and later their own 606 series. By 1949, the switcher market wasn't wide open. It was already being carved up by 3 established builders with proven products and, critically, parts and service networks in place. This was the market Lima entered. They were late, undercapitalized, and trying to compete against companies that had spent the better part of a decade building diesel expertise. But Lima had one advantage. They knew how to build locomotives. The question was whether that would be enough. Lima Locomotive Works had spent the 1930s and early 1940s at the forefront of steam development. Their superpower concept, high boiler pressure, large fireboxes, advanced valve gear had influenced steam design across the industry. The 284 Berkshire type, which Lima had introduced in 1925, became one of the most successful freight locomotives in American history. Lima knew steam. They had refined it to a level of efficiency that seemed unbeatable. But by 1947, even Lima's management could see the future. Steam locomotive orders were collapsing. Railroads that had been loyal customers for decades were suddenly placing orders with EMD and ALCO instead. The writing wasn't just on the wall, it was in the order books. Lima needed to build diesels or exit the locomotive business entirely. The problem was that Lima had no diesel experience. They had no engine designs, no electrical components, and no service infrastructure. Building a diesel locomotive from scratch would require partnerships, and Lima pursued exactly that strategy. They turned to the Hamilton Engine Company for the prime mover and Westinghouse for electrical equipment. Lima would build the car body, frame, and trucks, the mechanical elements they understood. This three-company partnership was unusual but not unprecedented. Baldwin had used de la Vergne engines early on before developing their own. What made Lima's situation different was the timing and the scale. Lima wasn't building diesels alongside a robust steam business. They were transitioning during a market collapse. There was no cushion, no room for error. The Hamilton Engine Company was a logical choice in some ways. Hamilton had been building industrial diesel engines since the 1920s, primarily for stationary and marine applications. Their engines were known for decent fuel efficiency and solid torque characteristics. For the LS1000, Hamilton supplied the T89-SA engine, an 8-cylinder, 4-stroke design rated at 1,000 horsepower. On paper, it was competitive with EMD's 567C and ALCO's 539T in the power range Lima was targeting. Westinghouse provided the electrical components, the Type 368 main generator and 362 traction motors. Westinghouse had been building electrical equipment for locomotives since the early days of electrification, and their components were well regarded. The 362 traction motors, in particular, were considered robust and capable of handling the high tractive effort demands of switching service. Lima's engineering team designed the LS1000 with switching service specifically in mind. The frame was heavier than EMD's equivalent, more steel, thicker members, designed to absorb the shock loads of coupling and shoving cuts of cars. The car body was conventionally styled with a center cab, but Lima gave it larger windows than typical EMD switchers, better insulation, and what operators would later describe as a more spacious interior. The fuel tank was generously sized at 2,100 gallons, giving the locomotive extended range for industrial service where refueling facilities might be limited. The first LS1000 rolled out of Lima's plant in 1949. It was marketed as a direct competitor to the EMD SW7, same horsepower, same intended service, but with what Lima claimed was superior build quality and durability. The price was competitive, sometimes slightly lower than EMD, for railroads looking to diversify their diesel roster, or for smaller roads that didn't want to be completely dependent on EMD. The LS1000 seemed like a reasonable choice. The LS1000 wasn't a copy of anything EMD or ALCO was building. Lima approached the design with their own engineering philosophy, shaped by decades of building steam locomotives. That shows in both the strengths and weaknesses of the machine. Start with the Hamilton T89-SA engine. This was an 8-cylinder, 4-stroke design with direct fuel injection. It operated at a lower RPM than EMD's 2-stroke 5 and 6/7 engine, which gave it excellent torque characteristics at low speeds, exactly what you want in a switcher. The engine's 4-stroke cycle meant it was theoretically more fuel efficient than a 2-stroke, and in controlled testing, the T89-SA did show better fuel economy numbers. The problem with the Hamilton engine wasn't the basic design. It was reliability under sustained railroad service. The T89-SA had been developed primarily for stationary and marine applications, where operating conditions are more controlled. In a locomotive, the engine faces constant load cycling, vibration, temperature extremes, and the kind of abuse that comes from being slammed into emergency throttle positions multiple times per shift. The Hamilton engine struggled with this. Crankcase fatigue became a recurring issue. Main bearings would develop problems under continuous heavy load. Cold starting in northern winters was notoriously difficult. The engine's combustion chamber design and starting system weren't optimized for sub-zero temperatures. These weren't catastrophic failures, but they were frequent enough to frustrate maintenance departments. An EMD 567 engine was nearly bulletproof. You could abuse it, neglect it, run it low on oil, and it would keep running. The Hamilton engine demanded more careful maintenance and attention. For a railroad trying to minimize operating costs, that difference mattered. The Westinghouse electrical gear was more successful. The Type 368 generator was a solid piece of equipment, and the 362 traction motors proved durable in service. Westinghouse had designed these components for the high torque, low-speed demands of switching, and they performed well. The motors delivered good tractive effort at low speeds and handled the thermal stress of extended shoving moves without overheating. However, Westinghouse equipment came with its own complications. The maintenance procedures were different from General Electric's components, which were standard on EMD locomotives. Railroads that already had EMD and ALCO units in their fleet had electricians trained on GE systems. Westinghouse used different control circuits, different troubleshooting procedures, and different replacement parts. This meant additional training and additional inventory, both things railroads wanted to avoid. Lima's frame and car body design reflected their steam-era manufacturing culture. Everything was overbuilt. The frame used heavier plate steel than EMD's switchers. The trucks were massively constructed with thick castings and robust spring rigging. The cab structure was welded with precision that impressed railroad inspectors. Operators noted that the LS-1000 felt solid. It didn't rattle and shake like some early Baldwin switchers, and it absorbed the impact of coupling operations better than lighter frame competitors. But this robustness came at a cost. The LS-1000 weighed more than an EMD SW7 despite having the same horsepower. That meant higher material costs for Lima and slightly higher rail wear for railroads. The heavier weight also limited where the locomotive could operate. Some industrial sidings with light rail couldn't handle the axle loading. EMD had optimized the SW7 to be as light as possible while still being durable. Lima built the LS-1000 to be durable first, with weight as a secondary consideration. The cab layout was one area where Lima clearly paid attention to crew comfort. The engineer's position had better sight lines than early EMD switchers. The windows were larger, giving better visibility when backing up or spotting cars. The control stand was logically arranged, similar to EMD's layout, but with some improvements. The throttle had a more positive detent feel, and the brake stand was positioned where it could be operated without the engineer leaning forward. Insulation was notably better, reducing noise levels in the cab. These weren't revolutionary features, but they were appreciated by crews who spent entire shifts in these machines. The LS-1000 failed not because it was a bad locomotive, but because Lima was fighting battles it couldn't win. The first was timing. By 1949, EMD had already sold thousands of switchers. The SW7 was a proven commodity. Railroads knew its maintenance requirements, knew its capabilities, and most importantly, had already invested in parts inventory and mechanic training. Buying an LS-1000 meant starting over, new parts to stock, new troubleshooting procedures to learn, new service relationships to establish. This is the orphan locomotive problem, and it killed Lima's diesel program. Railroads in the late 1940s were consolidating their locomotive fleets around a few standard types to minimize complexity. They didn't want diversity. They wanted standardization. Even if the LS-1000 was slightly better than an SW7 in some respects, it wasn't different enough to justify the operational disruption of introducing a new type. The three-company structure created its own problems. When an LS-1000 needed service, who was responsible? If the engine failed, that was Hamilton's problem. If the electrical system failed, that was Westinghouse's problem. If the frame cracked, that was Lima's problem. But a railroad shop foreman didn't care about corporate divisions. He needed the locomotive fixed. The fragmented responsibility made service coordination difficult. Parts had to be ordered from 3 different suppliers. Warranty claims involved 3 different companies. Technical support required coordinating between 3 engineering departments. Compare this to EMD. When an SW7 needed service, you called EMD. They built the engine, they built the electrical system, they built the frame and trucks. One company, one phone call, one parts order. EMD had field service representatives who could be on site within days. They had parts warehouses strategically located across the country. They had published maintenance manuals that were clear and comprehensive. Lima, Hamilton, and Westinghouse never achieved that level of integration. The Hamilton engine's reliability issues became a serious liability. Word spread quickly in the railroad industry. Mechanical departments talk to each other. Trade journals report on locomotive performance, and railroad management pays attention. When railroads started experiencing frequent bearing, failures, and cold start problems with the Hamilton engine, that information circulated. EMD's 5 and 67 engine, by contrast, had built a reputation for near indestructible reliability. Given the choice between a proven EMD product and a Lima switcher with a questionable engine, most railroads chose EMD. Lima's lack of a service network was crippling. EMD had spent the 1940s building not just locomotives but infrastructure, parts depots, training programs, field service capabilities. When a railroad bought an EMD locomotive, they were buying into a support system. Lima had none of this. If an LS-1000 broke down, the railroad was on its own unless the problem was severe enough to justify shipping the locomotive back to Lima or bringing in specialists from Hamilton or Westinghouse. For a small railroad or industrial operation, that level of support risk was unacceptable. Production numbers tell the story. Lima built approximately 55 units, combining the LS-1000 and its higher horsepower variant, the LS-1200. Compare this to EMD, which built over 500 SW7s between 1949 and 1951 alone. Lima never achieved the production volume needed to spread development costs, build an efficient supply chain, or establish market presence. They were building switchers in dozens while EMD was building them in hundreds. The final blow came in 1951 when Lima merged with Baldwin to form Baldwin-Lima-Hamilton. This merger made sense on paper, combining Baldwin's diesel experience with Lima's manufacturing capacity. But in practice, Baldwin had its own struggling diesel program. Baldwin switchers used their own 600i6 series engines and had their own reliability problems. The new company decided to consolidate around Baldwin's existing designs rather than support Lima's LS-1000. Production stopped. The LS-1000 became an orphan, not just in the marketplace, but within its own company. Despite its commercial failure, the LS-1000 wasn't without merit. Railroads that operated them successfully found things to appreciate. The rugged frame construction meant these locomotives lasted. When properly maintained, an LS-1000 could handle decades of hard service. The weight distribution was well balanced, giving good adhesion and reducing the tendency to slip on wet or icy rail. The low-speed handling characteristics were excellent. The combination of the Hamilton engine's torque curve and Westinghouse traction motors gave smooth, controllable movement when spotting cars or making kicks. Crew comfort was genuinely better than many competing switchers. The larger cab windows, better insulation, and thoughtful control layout made a difference during long shifts. In winter, the cab heater worked well. In summer, the ventilation was adequate. These might seem like minor points, but for crews working in these machines day after day, comfort mattered. Several railroads did operate LS-1000s successfully for years. The New York Central rostered a handful for yard service. The Nickel Plate Road used them in industrial switching applications. The Chicago and Northwestern operated them in branch line service. These railroads made the support structure work, either by maintaining close relationships with Lima's service department or by developing in-house expertise. Some industrial operations, paper mills, steel plants, large manufacturing complexes, bought LS-1000s and kept them running for decades because they could afford to stock parts and train their own mechanics. The LS-1000's design influenced later switcher development in subtle ways. The emphasis on cab ergonomics, the use of heavier-duty frames for industrial service, and the modular electrical cabinet layout all appeared in later designs from other builders. EMD's SW900 and SW1200 models, introduced in the 1950s, incorporated some of the same thinking about operator comfort and robust construction that Lima had pioneered with the LS-1000. It's worth considering what might have happened if Lima had made different decisions. If they had started diesel development 5 years earlier, in 1942 or 1943 instead of 1947, they might have entered the market when it was still fluid. Early entry would have allowed them to build a service network gradually, establish customer relationships, and refine their designs before the market consolidated around EMD and Alco. If Lima had chosen a different engine supplier, perhaps developing their own diesel engine or partnering with a more railroad-experienced manufacturer, the reliability problems that plagued the LS1000 might have been avoided. The Hamilton T89-SA wasn't a bad engine for its intended applications, but it wasn't optimized for locomotive service. A purpose-built railroad engine might have given the LS1000 the reliability it needed to compete. If Lima had been willing to sacrifice some of their build quality standards for lower weight and cost, they might have been more price competitive. The LS1000's robust construction was admirable, but railroads in the late 1940s were focused on economics. A lighter, cheaper switcher that was good enough might have sold better than an overbuilt premium product. But these are all counterfactuals. In reality, Lima entered the diesel market too late, with too little capital, using a partnership structure that created operational complications. The LS1000 was a competent locomotive that never had a realistic chance to succeed in the marketplace it entered. By the late 1960s, most LS1000s were being retired. Parts scarcity was the primary issue. Hamilton had stopped producing the T89-SA engine, Westinghouse had discontinued the 362 traction motors, and Lima itself no longer existed as an independent entity. Railroads that still operated LS1000s were cannibalizing units to keep others running. Some were sold to industrial operations, where they could be maintained as unique pieces of equipment rather than fleet assets. A handful survived into the 1980s, primarily in industrial service. A few still exist today, preserved in museums or maintained by railroad historical societies. These survivors are reminders of an era when multiple builders competed in the American locomotive market, before EMD and GE consolidated dominance. The LS1000 represents a particular kind of failure, not of engineering, but of timing and market dynamics. Lima built a solid switcher using quality components and thoughtful design. But in the late 1940s, being solid wasn't enough. Railroads needed proven reliability, comprehensive support networks, and fleet standardization. Lima couldn't provide those things, and the LS1000 paid the price. It was a diesel switcher that arrived when the battle for the American switcher market had already been decided.